Okay, I think let's get started. Thank you very much, everybody, for joining us for the second installment of the Underwater Acoustic SIG monthly webinar. If you haven't joined before, this is a webinar that the early career coordinators from the Underwater Acoustic SIG put out. And the idea is that we combine two talks from similar themes together and then have a bit of a panel discussion afterwards. Today we have Usama Kadri from Cardiff University, and he's going to be talking about acoustic gravity waves and their theory and the applications of those. And then we've also got Jake Ward from NPL, and he's going to be talking about his laser piston phone for calibrating low frequency hydrophones. So I think without further ado, we will get started with Dr. Usama Kadri. Take it away.
All right, good afternoon, everyone. Good afternoon, everyone. I would like first to thank the organizers for the kind invitation. I want to focus on two main points today, really to give you an idea what acoustic gravity waves are. I will show you a flavor of applications. So to start with, surface gravity waves are the surface waves that you see in the ocean, the ones that you can surf. When we're dealing with surface waves, we normally ignore the compressibility of the water. Now the water, and that's important to keep in mind, the water is compressible. We ignore the compressibility because for any analysis, for many applications, the slight compressibility of the water won't make much difference. On the other hand, if you're swimming in a pool, you can speak underwater, you can hear sound, right? And sound is a compression wave, and it requires the medium to be compressed. So if you want to make an analysis for sound waves, underwater sound waves, then you need the compressibility of the water. But on the other hand, here the gravitational effect is not required. Unlike in the surface gravity waves, which are called surface gravity waves because gravity is the restoring force. In my research, I actually combine between gravity and compressibility. So the compressibility of the medium and gravity, they're both there. I do not neglect any of them. So the question is why? I'm going to answer this shortly. There were a few works in the 50s and after that dealt with the compressibility of the water along with the gravitational effects. Back to the question, why do we need acoustic and compressibility and gravity effects at the same time? So first of all, you can think of the acoustic gravity waves as the acoustic waves, the sound waves. It's just under the effects of gravity. And now back to the question, why we need that analysis, combining compressibility and gravity effects, which obviously would complicate the analysis. One of the places where you need that is when you have a submarine earthquake. The fault in the submarine earthquake can be tens of kilometers, even hundreds of kilometers in length. That generates very long wavelength waves. The frequency is very low. At these lengths, gravity could modify the properties of the generated waves. Not only the acoustic gravity, but you can also think of the gravity, surface gravity wave, the tsunami, for example. We could also call it gravity acoustic, which means a gravity wave, surface gravity wave with a small correction due to the compressibility of the water. Another place where you need actually the both compressibility and gravity effects is if you're dealing with the interaction of gravity waves with acoustic waves. Now, why we would do that, that's another question. But obviously, if you need to analyze the interaction between acoustic waves and gravity waves, you have to include both gravity effects and compressibility of the medium, in this case, the water. When you have an impacting object on a surface, the water surface, that can generate acoustic gravity waves, which could have some details on the location, for example, of that impacting object, right? If we're able to analyze the sound that is generated from the impacting object. Okay, so in fact, any disturbance in time and space can generate acoustic gravity waves, right? So you can think about it as the analysis where you include both gravity and compressibility of the medium. Doesn't matter how slight compressibility is and how small the gravitational effects are. Now, when we solve the acoustic gravity wave problems, we deal with boundary value problem. You're going to see a few equations here, and if you're following, if you know what these equations are, that's completely fine. If you don't follow, that's also completely fine. So the idea is not really to analyze the, to look into detail of the equations, but I'm using the equations to help me give the message of the physics behind them. So what you see here at the top, mu is is a small parameter which controls the effects of gravity, which is given by the gravitational acceleration g, relative to the compressibility, which is given by c here, which is the speed of sound in water. So you see it's g over c squared. Mu is a very small parameter. We solve the wave equation. In this case, the wave equation is nonlinear. You don't have to solve the nonlinear wave equation. You can solve also the linear wave equation, but you need the full linear wave equation in order to get acoustic gravity waves as well. If you take mu very small, if you take that to the limit, then you end up with a Laplace equation that would only give you the analysis for the gravity wave, and you won't be able to analyze the acoustic gravity waves. So the least is that you need all the linear terms. We have boundary conditions at the surface, at the bottom. In this case, it's a free surface boundary condition. It's nonlinear. Again, it doesn't have to be nonlinear. It depends on the scenario that you're analyzing. And it doesn't have to be free surface. You can analyze also elastic, for example, if you have ice sheet at the surface. At the boundary, in this case, this is the simplest possible boundary condition at the bottom, which basically says that there is no penetration it's a rigid bottom. But it doesn't have to be the case. We can also analyze scenarios with elastic. It just makes things a little bit more complicated. Okay, so when we solve the linear solution, again, don't look at the details here. If you can follow the details, it's fine. This is a separation of variables. This is the standard way of doing it. But we end up with a dispersion relation, which relates the frequency of the waves with the wave number. Okay? And what we find is that the first solution for the first mode, for the dispersion relation, is it's basically the gravity wave, the surface gravity wave. And the next solutions would be, you have a countable infinity, actually, of solutions that are for the acoustic gravity waves. Now, you can have different numbers of acoustic gravity waves depending on the conditions, on the depth and other details, which is not so important right now. Now, so let's go back to the question, what are acoustic gravity waves? Let's compare that with surface gravity waves that we can see at the ocean, and let's take a pressure field, for example. So if I take the pressure field at the surface of the water, what I see is that because of the pressure is decreasing exponentially with the depth. If this is in meters, so this is just 4 meters. If you're swimming here really, and there's a shark there at a depth of 4 meters, the shark won't even sense the pressure field that is produced from it. Now, just don't try that, because it might have other sensors to find out that you're actually swimming at the surface. But the idea is that even if you had very huge storm and you're 100 meters below the surface, you don't feel anything from that storm. Okay, the scenario with the acoustic gravity waves is completely different. And here we look at the complete depth of the ocean, and we take an average of 4 kilometers. So this is no longer in meters, the z-axis here, but it's in kilometers. And what you see here is that this is a periodic motion that spans all the entire depth. Okay, so that shark might actually have some sensors that can sense these acoustic gravitational waves. So it might actually find out that you're swimming at the surface because of something like that. Okay, so the next thing that you can look at is the trajectories at the surface. Again, with surface waves, the trajectories, you have what is called the Stokes drift. So the wave is coming from left to right, and the particles are actually drifting. They're moving from left to right. But this movement decays exponentially as you go with them, just like the pressure scenario, right? This is not the case with the acoustic gravity waves. If you look at different depths, right, even as you see at 3,500 meters, at any depth you can have this kind of movement. It's much smaller. It depends on the source, of course, but it can be millimetric, and it can be maybe in centimeters if the source is very energetic, and it can be much less than that as well. Depends on the source. So you do have this movement everywhere. And the last thing that I want to show to compare between the two types of waves, surface gravity waves and acoustic gravity waves, is the speed. If you have a submarine earthquake, for example, well, you can have elastic waves, right, in the seafloor, but you would generate acoustic gravity waves, okay, along with the tsunami. But the acoustic gravity waves travel at speeds, the sound speed in water, which is 1,500 meters per second, which is much faster than the tsunami. So just to give you an idea, by the time that the tsunami moved 100 kilometers, acoustic gravity waves would have moved 1,000 kilometers. So you can think of this as not separate really waves, but waves from the same family. It's just they have a little bit of different properties. So they come from the same source, and they carry information about that source. And this is something that we would want to make use of. But let's look at this scenario also. Now, the last column that you see is actually when the floor elasticity is considered. So instead of having 1,000 kilometers in distance, you can get 2,000 kilometers in distance. So doubling the speed almost, right? So they couple with the elastic floor, and as a result, the speed becomes similar to the speed of sound in the elastic wave. So this propagation has very high speed relative to the tsunami, and we would be using, I will show you here, for an early detection of tsunamis.
Sorry, Sam. Oh, yep. we lost your audio briefly, but I think you're back.
I'm back. Okay.
You're back.
All right. So you've heard the part about the elasticity? Can you hear me?
Yes,
okay.
We only missed about 10-15 seconds of your last slide.
All right. Okay. Yeah. So I actually put this slide just to give me a break. So this was...
A tsunami is a series of waves caused by the displacement of a large volume of water. Waves can surge as high as 100 feet and devastate coastal areas. Tsunamis are mainly caused by underwater earthquakes and are currently detected using pressure sensors and buoys. However, the system relies on a tsunami physically reaching a buoy to trigger an alarm. Scientists at Cardiff University in Wales have found that an early warning system can be developed by using a hydrophone to record acoustic gravity waves radiating from an earthquake. The waves carry information about the earthquake and can be used to determine the characteristics of a forthcoming tsunami, allowing for early detection.
So a hydrophone is an underwater microphone which can record the signals that comes from these acoustic gravity waves. And in order to be able to, so the idea is quite simple. So if you have an earthquake and you have the tsunami front, the acoustic gravity waves travel much faster. So if you have this hydrophone somewhere located within a radius of, say, 1,000 kilometers, then you might be able to use that for an early warning system. However, in order to do that, you need to analyze the scenario almost in real time. And for that, we developed first a Slender fold approach. So we look at the float as a cylinder, and that helps us in developing a closed form solution which is analytical, right? but you can do much more than one fold actually, because it's a linear solution. You can combine different folds together, and you can have different shapes and different times and different properties as well. Now this slide here is just to give an impression of the comparison between the theoretical model. So you have different points here. It's from a real scenario, but I don't remember which earthquake really. But you have 4 different points here, which correspond to A, B, C, and D. We're looking at the pressure here, time series for the pressure. This is in black is the current model, which is the theoretical model, and the blue is the numerical model with the constant depth, and the last one is with the actual depth, the variable depth. And you can see that at the different points, the theoretical model is capturing quite well the main signature. Okay. This is another example which shows that for the maximum pressure, you can have this is for the constant depth with the current model. With the theoretical model, it's almost carbon copy of the numerical solution, right? And with the variable depth, you start seeing some reverberation effects, but that's not really important if you're looking at the very first arrivals, because the reverberation effect becomes more distortive when you have longer time and so on. So if you're interested in the early tsunami warning system, you really want to take the first parts of the signature in order to analyze the system. Okay. So, and we need to have some kind of solve the problem inversely, right? So basically what you have here is the closed form solution for the pressure, and you get that pressure, right? The P1 here, you can get that one from the signature here. So you actually have that in the hydrophone, but you have all these unknowns, right? You have all these unknowns for the speed, horizontal location, width, all the geometry and duration, basically, of the geometry and dynamics of the fault. Which we use some analytical and semi-analytical techniques in order to retrieve. Okay, the nice thing about the inverse problem solution is that it's a probabilistic approach, which convergence as it's running, so it can give you real-time idea of what's going on, and as time is passing, it converges more and more, and gives you more confidence in the solution. Just to give you an example here with numbers, there are different cases here. For example, case C, this is the input and retrieved parameters, and you see that the retrieved parameters are very close to the input parameters, but most importantly is that the times that it takes. So we're talking about almost 3 minutes to make the complete analysis of having the signal analyze everything and have the and actually be able to say if you have a tsunami, you can have a tsunami or not, and depending on the location and so on. Okay, the other application that I want to show you is very briefly really, is that you can use that also for impacting object, and this is one place we looked at for the missing MS-370 flight. This is now, I think it's 7 years already, and it's still missing. Amazing. So we in this problem we were able not only to use hydrophones. With a single hydrophone, we're able to analyze and give a location. So normally the way you do it is that you need to make something which is called frangulation. You have different hydrophones at different locations. Each hydrophone from the same signal will give you some kind of radius, and then where all these you can think of a circle where all these circles meet in a point, 3 circles in a point, that would give you the location of the signal. But here we were able to also have a technique by analyzing the evolution of the frequency that gives you the location of the signal. Okay. One quick possible application, as if you, as I said, that there was the acoustic gravity waves can make some movement in all the depths. So this could be important for things like nutrients transportation and salts. So it might be important for microorganisms. A small experiment that we had a few years ago with the acoustic transducer, which you can see here. Let me run this. This is just a water tank, and these particles inside, they are neutrally buoyant particles, and you see now it's working actually, and you can see that there's this movement in the particles. Okay, just to illustrate the effect. All right, now getting to the problem with nonlinear interaction. I'm going to go quickly on this. The main thing that I want to show you here really is that you can have this interaction between gravity and acoustic waves, but for that you need 3 different waves. These 3 different waves can be acoustic wave. This is the amplitude of the acoustic wave, or the gravity waves, and then 2 gravity waves. So 1 acoustic wave and 2 gravity waves, which is S plus and minus. And they can interact non-linearly, and they can share energy together. You can actually see this by this evolution of dAdt, which is the evolution of the amplitude in time, which is related to the interaction between the 2 other waves. It's always an interaction with the other 2 waves. Okay. Now, why is this important? Let's look at these 2 cases. Here you have this share between 1 gravity and the 2nd gravity with the acoustic mode. So the 2 gravity waves can start generating the acoustic mode. You can see this here. You start with this amplitude here and here for the gravity waves, and you start with 0. So there's no amplitude, there's no acoustic wave at the beginning, but the acoustic wave can actually start feeding up by energy, taking energy from the gravity waves. And we can think of the other problem where you have 1 gravity wave and 2 acoustic modes. Okay, in a similar way, they would start sharing energy together. So this could be an idea for tsunami mitigation, right? We don't have the technology for any of the things that I'm going to show right now. It's just a theory. So you have a tsunami, and imagine that you had the technology to actually create these acoustic gravity waves, the 2 acoustic gravity waves, to interact non-linearly with the tsunami. You have to do it carefully, otherwise you can make a small tsunami into a huge tsunami as well, right? So you need to know everything about the tsunami, which we don't know yet, so we're not there yet. But the idea is the following. You have this tsunami, which starts with this amplitude, and it's traveling from right to left. This is the shoreline here on the left side. And you can send 2 acoustic gravity waves that interact with the tsunami, and as they interact, they start pulling energy from the tsunami, and then because they're moving faster, they would actually move away from the tsunami period. And you can think about it as the redistribution of the tsunami over a larger space, okay? Which means that you have smaller and smaller amplitude of the tsunami. And if you have enough time, then you could reduce the amplitude of the tsunami in a way that the impact on the shoreline is reduced. Okay, the last thing I want to show is the time reversal. That is also this interaction between 2 gravity waves and acoustic mode. If you allow this acoustic mode to be just a standing mode, so it's not propagating anymore, it means that you would have a evolution equation with an acoustic mode which goes up and down, right? You can think about that just like a tank which is moving up and down. That gives an evolution of standing waves, like Faraday waves. So if you send a wave from left to right here, it's just a wave function that I put here. So at some point, at some time, you just make it interact with the acoustic wave. It generates exactly a similar gravity wave, a second one, which is in red here. The amplitude depends how much energy you put in the acoustic wave, but it's opposite in the amplitude, but it's opposite in the direction. And yeah, so the other things that I cannot show here today are the things that might be related to quantum mechanics. Many special thanks to many people, many collaborators and students that without them, yeah, many of what you've seen today couldn't have been done. But the main message that I want to give is that acoustic gravity waves brings these really 2 elements from 2 different fields that are virtually decoupled, right? The compressibility and from acoustics, and the gravity effects. You put them together, and that, first of all, that brings many researchers from diversified backgrounds all together, and that where you can have more general way of looking at the applications that you're analyzing. Thank you.
Thank you very much, Usama. That was fascinating. When I first came across your research, I knew you were interested in tsunami detection, but I didn't have any idea that you had ideas for tsunami mitigation. That's really interesting.
Thank you.
So if anyone has any questions, we're going to do a Q&A session at the end as a sort of panel discussion with Usama and Jake together. So if you have any questions, if you put them in the chat or the Q&A, then we'll get around to them after Jake's presentation. So up next, we have Jake Ward from NPL. And when you're ready, Jake, if you could share your screen and we can crack on. And you are currently muted.
Okay, have I managed to A, unmute myself, and B, share a screen?
Full marks, Jake. You're all there.
Excellent.
Thank you very much.
Okay, so leading on from Usama's excellent presentation there on acoustic gravity waves, I'd like to present some work that we've kicked off this year on a project called Infra AUV. So my name is Jake Ward. I work at the National Physical Laboratory. Thank you for inviting me to the Specialist Interest Group meeting today. It's very good to be here. And also, I'd probably like to say that it's a very exciting time to be working in underwater acoustics. For all the attendees, I think there's both interesting opportunities in the environment and defense, and all sorts of interesting things going on in underwater acoustics. So it's good to be here. Thank you to the early careers coordinators, Ben Thomas, Ben Ford, Nikhil and Roslyn, for inviting me on. Okay, so this project's about infrasound, and in particular calibrating hydrophones at low frequency. So this is different from the frequencies we're used to. I guess our understanding as human beings of frequency comes from our hearing system, and we don't really know much about below 20 hertz from an experiential stance. So and so it's an interesting problem to calibrate hydrophones at these frequencies, because fundamentally the wavelengths are extremely long, and so we can't use the techniques of using tanks to transmit and receive sound. We can have to come up with different approaches to calibrating hydrophones at low frequency. So there are other candidate transducers for low frequency transduction. So there's microphones in air, or accelerometers, or geophones. So accelerometers measure acceleration, and geophones velocity. So moving coil devices have a voltage proportional to velocity rather than pressure or acceleration. So hydrophones, then nothing like Usama's equations here. This is more my sort of equation here. So the sensitivity of a hydrophone is the pressure. Sorry, that's probably wrong as well. The volts per Pascal. Sorry, that's upside down. There you go. So we're interested. Spotting the deliberate mistake. So we're interested in the volts we get per acoustic Pascal for a hydrophone. So the project then is this project in infrasound, Infra AUV, has partners across Europe here, and aims to come up with both primary and secondary calibration techniques. So what I mean by that is a primary calibration technique relates the acoustic Pascal, so force per area, to the International System of Units, so the SI. So here in the center of the screen, you have the previous definition of the kilogram was based on an artifact. And actually, you may or may not be aware that this changed recently. So we've redefined the kilogram. And as a side effect, I guess the Pascal's been redefined as well. And actually, the work I'm going to present today relates the acoustic Pascal to the wavelength of laser light and also the behavior of air, the thermodynamic behavior of air. So these are the project partners across Europe, Denmark, France, Turkey, the UK, all sorts of partners there. And the way the project's broken down is we split it up into air and sea and land. So NPL is involved in the underwater acoustics aspects. So we are interested in hydrophone calibration between 0.5 Hertz and 100 Hertz. And the airborne partners are even lower in frequency, down to 40 millihertz. And you could start to argue that ocean-going waves could be acoustic waves, and tying in with Osama's work. When we go for extremely low frequency, we start to hear the natural modes of the Earth's crust and ocean-going surface waves. So, and vibration seismic aspects of the project go down to 10 millihertz. So extremely low frequencies are there. So this is the full name of the project here. AUV, you may be surprised or disappointed to hear, doesn't stand for Autonomous Underwater Vehicle, as it often does in our arena. This is acoustics, underwater acoustics and vibration. It's how the project is defined, uses the same acronym, AUV, infra AUV. So what might be going on in the ocean at half a hertz then? Just to draw a line in the sand, I guess events that happen at half hertz, for example, one might be the heartbeat of the blue whale, happens once every 2 seconds. Interestingly, only when it's at the surface of the ocean. Kindly, Stanford University has said I could cite their work here, and interesting, the heartbeat of the blue whale reduces as it goes deeper. And another thing is human breathing is about half a hertz or 0.6 hertz. But actually, we're interested in using hydrophones to detect volcanic eruptions, earthquakes or tsunamis or nuclear explosions. So the Comprehensive Nuclear Test Ban Treaty is interested in calibrating hydrophones at extremely low frequencies and monitoring around the globe for low frequency events. So let me start to talk about the laser piston phone then. The laser piston phone, or a piston phone, is one of many options we have for calibrating hydrophones. So other options are available. And for anyone who likes British standards, there's an absolute epic here, 60-pager part 2 of BS 60565-2, part 2, is procedures for low frequency pressure calibration. So you can have a vibrating column, you can dunk a hydrophone, you can use hydrostatic excitation. You could is fundamentally introducing a change of pressure on the transducer. So a couple of reciprocity, where we have 3 devices within a closed chamber, and we transmit and receive on different combinations of them and measure voltage and current. So the laser piston phone is an exciting option. I swore I'd never get involved in optics. It's just not as good as acoustics. But I've ended up developing an interest in interferometers as well. So here is the chamber, if you like, with the sleeve removed. So this would be a cylindrical chamber, but I've peeled away the aluminium cylinder and shown the hydrophone here in the center, the piston. Can you see my cursor, could I ask? Yeah, excellent. So there's no point in me talking about what I'm pointing at if you can't see what I'm pointing at. So the piston, which moves up and down within the cylinder, and an actuator and an interferometer. And the sort of innovative thing about this is we're measuring the displacement from the back of the piston instead of the front of the piston. We're doing this because the wavelengths in water are just too long at 1 hertz. We're talking about 1.5 kilometer wavelength, and we don't have test tanks that big. I suppose we have the major oceans, but it's not easy to control that environment. So the laser piston phone works by squeezing some air, and we measure the displacement of the piston from the back with using the wavelength of laser light. So it's what is a laser piston phone? It's an acoustic calibration device with a circular piston driving a closed volume of air, and it's widely used in airborne acoustics to calibrate microphones, but here we're using it to calibrate hydrophones. And a key difference there, microphones can't typically tolerate hydrostatic pressure. Their oodle's more sensitive than a hydrophone typically, unless you put an amplifier inside the hydrophone. And NPL's been working on this. There's a paper in Metrologia, 2007. Richard Byram is a collaborator on this project, and used to work at NPL and published this work on laser piston phones for microphone calibration. So we're going to squeeze the air in an aluminium chamber and measure the amount of squeezing by displacement. And we have an actuator there. There's a impedance analyzer for the actuator we're using. It's piezo ceramic, multi-layer piezo ceramic, and the volume of the chamber is just 390 milliliters, so a can of beer, if you like, of air with a hydrophone in it. And here you can also see we have the ability to pressurize the hydrophone with an air feed, so that helps pin down the equation, actually, because the equation involved in interpreting the displacement of the piston to the pressure in the chamber involves the atmospheric pressure, so 101 kilopascals at sea level, and also gamma, which is the ratio of specific heat for constant pressure and constant volume. And so the pressure is a function of the change in volume, which we get from the displacement x, the interferometer, and the diameter of the piston, and v, the volume of the chamber. So we can transmit a tonal signal. So just to show a setup with the hydrophone and microphone in place, here the interferometer we're using actually is something called a quadrature interferometer. So it uses two polarizations of light for, if you like, a sine and a cosine channel. So previous work that I published in 2019 used integer fringe counts, so 330 nanometer steps, but with a quadrature interferometer, we're able to get sub wavelength of light accuracy on the measurement, and I'll explain more about that later. So here we have a hydrophone, the thick cable, and a microphone in the same chamber. A laser looks rather unimpressive there, hitting a beam splitter, and a reference mirror and an observation mirror looking up towards the bottom of the piston. So we capture signals on the oscilloscope. Here I'm using the picoscope, an 8-channel version. So we have a sine and cos channel, and interestingly, they are chirp signals for a sinusoidal drive of the piston. The fringe counting interferometer is a chirp. So as the velocity increases, the rate of change of light intensity changes. So so we can unwrap the phase of that to give us displacement. And here we have the actuator drive signal in gray, microphone in purple, and hydrophone with some 50 hertz noise. This is intentionally low drive signal, so poor signal to noise ratio to show 50 hertz noise coming from the mains there for a 500 milli, 900 millihertz drive signal. So we can now, with the interferometer, we can relate the drive voltage to the displacement in nanometers, sorry. So we're getting 100 nanometers per volt on the drive there, and we've unwrapped the phase of the quadrature interferometer. So just to show you the lab setup, then we have here I'm showing the test where we compared the front and the back. So there's a subtle difference in displacement on the front of the piston to the back of the piston arising from the spring mount system that we use. So here I'm comparing, so we get a circle on the oscilloscope for each interferometer. So we've got an interferometer looking down at the piston from the top and an interferometer looking up at the rod that drives the piston at the back. And actually, we also did some scanning laser Doppler vibrometry on the front of the piston as well, because I was interested in the coplanarity. So these are laser measurements across a grid that show us the displacement of the piston, and we can fit a plane to the maximum of the stroke and the minimum of the stroke and compare the angles. That was one of the interesting checks that we wanted to make, was how much is the piston rotating and would it affect our measurements. Another interesting point is the linearity of the drive. So we drive it at different voltages and check that the displacement is scaling with the drive voltage. So the Quadrature Interferometer, I have enjoyed working with lasers. It's very much as fun as it sounds. And I liken this Quadrature Interferometer to a corkscrew. So if we have two orthogonal beams of light or interferometers, then we have a sine channel and a cos channel, and each fringe of light is like a rotation of the corkscrew. And we can accumulate the phase, so we can from the phase of the interferometer infer the displacement to sub wavelength. So the wavelength of light we're using is red. It's 630 nanometers, and so each fringe is half that, 300 nanometers ish, and we can get down to about 30 nanometers accuracy with the noise on the electronics. So, and like I said, for a sinusoidal drive of the displacement, that's actually a chirp in the frequency domain of the photodiodes in the system. So as the velocity increases of the piston, we get more fringes per second. And so this is a nice plot of the spectrogram of the photodiode signal as we drive it with a tone burst of 10 cycles. And as I was saying, we compared the front and the back of the piston, and we can see that we can infer the displacement of the front of the piston from measurements at the back. So that means we don't have to pass laser light through the chamber, which has its own gotchas, which are the optical refraction index of air changing with pressure, which we'd rather avoid. So here we're comparing the front and the back displacement over numerous octaves, about nine octaves there, from 125 millihertz up to 500 hertz or so. So that's all I wanted to mention on that. And so I can compare them, as I showed you, the microphone and the hydrophone in the same chamber. We can compare the voltages between those, and we can take the results from another national metrology institute in Denmark, and we can take their results, and we're interested in moving down in frequency to below 1 hertz here. And so this compares a microphone sensitivity to a hydrophone sensitivity, and that's where we're going with Infra AUV, which is a 3-year project. So in summary, there's calibrations have been performed over 9 octaves. We scanned the front face to investigate coplanarity. We characterized the actuator in terms of nanometers per volt and compared to a microphone. And we're looking forward to lots more work in this arena. So hopefully that's explained a little bit about low frequency calibration of hydrophones. And just to acknowledge the funding mechanism, the full title of the project is here: Infra AUV Project 19EMV03, part of MPIR, which aims for infrastructure for metrology for Europe. So that was, and these are my colleagues at NPL who I've been working with Angus on the optics and the underwater acoustics group. So that was all I wanted to say, only to add football is coming home. Thank you very much.
Fantastic. Thank you very much, Jake. That was another fascinating presentation. Yeah, I was wondering, I'm going to use my prerogative as host to ask the first question. I was wondering if anyone has detected the heartbeat of a blue whale via acoustics, to your knowledge. Oh, you're muted.
So I'm only going to say anecdotally, I've not seen any quantitative results, but I guess it's one of the lowest frequency sources always there in the ocean. I'm not sure. I don't know if that's true. I've certainly never heard one, but I'm unlikely to ever hear one because it's only half a hertz.
Yes, you're probably in trouble if you can hear that. Super. And the other low frequency question at that end of the spectrum that I wanted to ask was, is it what is it that limits your calibration? Why do you have a lower limit in the underwater acoustics sort of part of your project? What drives the choice of that lower limit number?
Okay, yeah, great question. Thank you, Ben. So this is quite interesting actually, and we'll untangle this problem as we go ahead. But if I've understood correctly, what is the lower limit? So why can't we keep going down and down in frequency with a laser piston phone? And I think the answer is going to be, and I need to quantify this, but so sound as we know it is an adiabatic phenomenon. So that means as we squeeze the air or water or anything else, heat doesn't have time to flow in the period that the acoustic wave is propagating. But as you go lower in frequency, this isn't true anymore. So heat does have time to flow, and so in the example of the laser piston phone, when we squeeze the air, it inherently is heating it up by the thermodynamic properties of the fluid. And if we leave it long enough, the heat will flow into the aluminium chamber, and that would then, and if it returned to its original rest temperature, that would be an isothermal change. So isothermal compression instead of adiabatic compression. So to answer your question, the limitation comes from heat flowing out of the air into the chamber. And an excellent question it is too. Thank you.
Well, thank you very much for the thorough answer. Okay, well, I think I had better stop hogging the question time. So we have about just under 10 minutes to answer some questions. So I'm just going to the Q&A box. We have one question for Dr. Kadri. It's from Alexandra Padilla. She says, Dr. Kadri, great talk. I was wondering if you have worked on evaluating your models with controlled laboratory experiments using flow water tunnels with sediment beds. Also, can you elaborate on potential sources of error in the inverse method to calculate parameters of the fault?
All right, so two questions.
Let's start with the first one.
Oh yeah, they're both excellent questions. So with regards to the lab experiments, we haven't done as much as I would like to actually. There's so many controlled lab experiments that I want to do. Like one of the first that I would really like to do has to do with the nonlinear interaction between acoustics and gravity. That gives a nice lab validation of the theory. With sedimentation also, that would be I think a great thing, because one of the main thing that one of the main projects that we're working on is that acoustic gravity waves, try to quantify how much acoustic gravity waves can move things. It's not only in the water layer, right? But you can think about it not only in the water layer, but also at the bottom, right? So that might be another way to look into that. But yes, definitely. I mean, I would love to make much more controlled laboratory experiments. We do have quite some validations from field data, right, from CTBTO data, especially with the problem with the tsunamis, right, and also the MS370. But with the tsunami, with the problem with the early warning, not the mitigation. Right? The mitigation, we said that's, let's say, a different thing, right? That's a different technology, which doesn't exist. But for the early warning of tsunamis, yeah, we've been using, we have access to lots of, I mean, CTBTO data for the, I think tens of earthquakes, and we've been validating with that. Still, even for these, even if we have good validation with the with data field, I would love to do also controlled laboratory, because then that can actually take you to the fundamentals of the physics. You can start playing with the parameters the way that you want, and then so there's lots of room to do that. Regarding to the other question about the inverse problem, now I just want to make one point clear here, which is the last thing that I want to do really is to try and find out the actual geometry of the fault. I don't care about the actual geometry of the fault. What we really after, for the application, of course, for the specific application for the tsunamis, what you really want is to think about what makes a tsunami, right? To have a tsunami, you need to have that water elevation of the lots of water in the vertical direction. That what would create a tsunami. So what we're after is some effective dynamics and effective geometry of a fault. And this is sometimes a place where if I'm discussing this with people, they say, well, wait, but it's much more complicated than a rectangle, right? We don't care. It's because we're not looking at the actual dynamics of the Earth. At the end of the day, you have some effective uplift of the water. And the question is if that effective uplift can be considered as a slender fault or many slender faults. That's a different question, right? Not in all scenarios you can have that. So this is one point that I wanted to emphasize. So we're looking at some effective fault that would result in the vertical motion. So any part of the actual movement of the fault which is not effectively upwards, we don't care about that, okay? That's important to note because that means that the potential errors are different, okay? So we don't really care about how the exact location and what is the potential errors come from different places. One of the main when we do sensitivity analysis, we see that one of the main places where you can get errors is in the how much frames you have when you make the frequency analysis, right? So if your recordings are, now I don't remember now exactly how much it should be, but if you have very fine frames per second, then that can enhance the results, okay? And you can understand that because you have that the evolution, right? So you can have more finer description of the evolution of the frequency. So this is one of the main sources. Now there are other sources, like if you have if the fault is complicated, so you have multi-faults and so on. But this is something which is doable. We didn't do that yet. It's manageable because there are two questions here. It's either that the multi-faults can be at separate times, quite separate times, which means you don't really care because you have some arrival at the beginning, right? Which you can start analyzing, and then as you analyze more, you can get also the arrivals of the from the next faults. So you can think about that as different effective faults that you're analyzing separately, okay? Which is something that we're still not there yet, but this is something that I think it's manageable. The problem is that when the times become closer and closer, so the signals start to overlap on top of each other, the main signals, the main arrivals, the first arrivals start to overlap on each other. Then the question of the depth becomes important, and if you have variable depth and things like that become important. The other source that would be important is if elasticity has to be considered or not, and that has to do with the topography. Because if elasticity is important, that has to do with the depth. So just to give you a quick introduction to that, if the depth is not large enough, only the first acoustic mode survives, and the other modes dissipate. Okay. But it survives because it couples with the elastic floor, which means the speed now at which it propagates is much higher. So you need to know the speed at which these acoustic modes are arriving in order to be able to correctly use the inverse model.
So I wanted to pick up on this, the coupling between the acoustic gravity wave and the elastic seafloor. I noticed in your plots you have the low amplitude sort of coupled wave arriving before the acoustic gravity wave itself confined in the water. I wondered if you use that as a sort of primary, yes, the tsunami is coming, and then the second arrival of the larger amplitude section as a, yes, it's really coming, a sort of confirmation. But I think you said that your estimation uses the ongoing signal to improve its estimation. So yeah.
That's an excellent question. The way that this is one of the main projects that we're working on, right? The early detection of tsunamis, and the way that we're building the project is to make things integrated together, right? So I mentioned, well, the video actually mentioned buoys dart buoys at some point. The idea is that we can make use of any data that is available there. So you can make use of seismic data, right? That will give you the location. That's one way to, let's say, one way that we can make some corrections also as the calculations are running, right? So you know the location, you can recalculate it from the hydrophones, for example. But just as you said, the arrival of in the elastic layer, right? That can be earlier. So why not? We can also use that in order to have an earlier, right? So start with the process. The earlier you start with the process, the faster you're able to start confirming, right? And you can. And this is the way that we're building it. If you have, this is the way that I imagine it, is that if you have some data coming from dart buoys at some point, you input that data to the system, and that helps in calibrating what's going on and confirming. So it's the last thing that we want to do is something that replaces anything that is out there. It's actually, we want to make use of everything that is out there, make efforts to put things together. So definitely having the measurements from the elastic layer, that would be a great place to look at. And I think one of the good research possibilities to look at is actually to start looking also at these gravitational effects in the elastic layer. Okay, we started to look at that in the direct problem, I call it. So we look at analysis for when you have a source and it starts propagating in the elastic layer, but we didn't develop yet an inverse problem for the elastic layer, which should be this should be different than the one in the water layer. But having these together is definitely the way to go forward. So to get the information as fast as possible, right? And then start building confidence in whether you have an alarm, you should send the alarm off or not.
Great, thank you very much. We should probably wrap up soon. I'll give just a little bit of extra chance for anyone to ask a question in the Q&A if they want to, before people start heading off. But I think since we've used up our hour, I think it only remains for me to thank very much our speakers, Dr. Usama Kadri and Dr. Jake Ward. Say thank you very much to everyone who's attended. The webinar will be recorded, or has been recorded, and will be available on YouTube very soon. So if you know that someone's missed it and they would enjoy it, then please spread the word. Next month's webinar is not confirmed yet, but is planned to be on the 29th of July. If you know anyone who would be interested to speak, please get in touch. And that is it. So yeah, thanks again, everyone, for attending, and enjoy the rest of your days. Thank you.
Thank you all.